Hi guys, this is my progress report 3, and it's of thermal fatigue analysis of a brake rotor in racing applications. So here you can see the constants in my project, and the first being geometry of the rotor. So ID, OD, anything with a dimension, that's going to remain constant. Under the thermal characteristics system, magnitude, ambient temperature, film coefficient, they're all going to be constant. Under the static structural system, applied force and moment are constant, and time is constant as well. And this serves as a comparison tool. So when I'm changing any kind of material property, I'll be able to examine the differences in any kind of plots of deformation, stresses, temperature distributions, and really analyze what is the best material for this instance or for like a high performing rotor. So knowing the constants and everything, I'm going to give you guys a brief overview of what I'm doing here in ANSYS. And here you can see there's two different systems, like I mentioned earlier, a steady state thermal system and a static structural system. And the first three categories, engineering data, geometry, and model, they're all hand in hand. They're constant, so they have the same values and the same everything. They're set up the same. What differs here is in system A, it'll carry out its simulation and its analysis um, under thermal states, and it will pass it on to the static structural system, and the system will consider this in its analysis, and you'll see later the plots are actually within that system as well. And here's my initial material, and that's structural steel, and I'll go back here and change that once I choose a better fitting material. So this is the initial geometry that I imported in the first video, and this is my sketch that I just created, and this is where the pad meets the rotor, and that created three different bodies. And here under model, you can see that the same different sections of the body that was created, from that pad to rotor interface. Here are the contact regions. And here under steady state thermal system, you'll see that I have my constants that I refer to. Here's the mesh, but here is where I set my initial temperature as 22 degrees Celsius, my time setting at 3 seconds. And here under heat flux, the magnitude is 23,451 watts per meter squared. This was applied to where the pad meets the rotor, so that surface. And here it was applied to the whole face of the rotor, but not the lip that you can see here. And that's at a film coefficient of 230 watts per meter squared Celsius and ambient temperature 22 degrees Celsius. And here, it covers the same areas or the same faces, and it has that same ambient temperature of 22 degrees Celsius under radiation. So now that it's completely set up, I solved it and I got my first plot, and this is the thermal plot, and I have my max and my min. Max of 99.3 degrees Celsius and my min of 73.8 degrees Celsius. Here you can see my total heat flux, and again it's my distribution here as well as a max and a min. And now considering this, we're going to move on to the static structural system. Same analysis system, but I applied fixed supports here, and there's 6 of them, and this is where the bolts would fit into the rotor itself. And here is the force applied from the pad to the rotor, both in the y and negative y direction, with a magnitude of 2,986 newtons. Then I applied a moment as well, and you can see in that shaded area right here that that is the only surface that was selected, and that's at a magnitude of 179.76 newton meters. And here is the imported temperature from system A, like I'd mentioned previously. So now being completely set up, I generated my total deformation plot with our max and our min. Um, and among the other plots, this is another good one that I can use as a comparison purpose when I select different materials. And here you can see my plot with the equivalent stress. So these are just still images that I use, and these are going to be the images, when I go ahead and I carry out, further analysis. I'm going to refer back to these. They're the same images as from, what you've previously seen in the video. But this is my temperature plot under the steady state thermal system. This is my total heat flux plot. This is total deformation, and this is under the static structural system. And this is equivalent stress. And again, I'm going to include these in my final presentation as my baseline results, and show any kind of improvement, when I create any more plots or any kind of generation. So a direction from here out, I'm looking to, further make sure that these constraints are accurate, per the scenario that I want to create. So I pulled these, different kind of data and entries from data from the Formula SAE team as well as Scholar articles, and I want to make sure that that resembles as closely as it can to what I'm trying to accomplish here. And once that's done, I'll go ahead and I'll change the material more to improve any kind of performance that I can of the cart rotor, and examine the effects of the plots that I have for my initial baseline. And from here I'll be able to verify and validate what's really the best option for this scenario, and hopefully carry this into real practice. So if you guys have any questions, feel free to let me know. But that's all I have for now. So I want to thank you guys for your time.